by 1910 or so, the atomic picture of the structure of atoms was established. That matter is atoms. Atoms have a tiny positively charged nucleus at their center, and that's surrounded by a cloud of electrons. And atoms could emit and absorb radiation in discrete packets called photons with a very, an energy related to their wavelength. We're going to demonstrate that in a second here. And the other really interesting thing to explain then is why atoms could only emit and absorb photons with such very specific energies. Now you've probably seen this. It's what we call the spectral emission lines for different atomic elements. Hydrogen, mercury, neon look like this. Here's the visible spectrum from around 400 to 700 nanometers from, Roy G. Biv, right? You've all heard that before. But Roy G. Biv goes in that direction. What we're going to do now is actually see these. And to see them, I'm going to hand out diffraction gratings to all of you. Here's one. You can scatter these around the room. As you get them, start practicing with them, looking at the lights on the ceiling, which are a little bit bright, so don't stare directly at it. You want to look off to the side of the light. When you look at the incandescent light, you can turn this thing 90 degrees and so forth, and you'll see, whoa, it's pretty bright, isn't it? Don't hurt your eyes. Don't hurt you. What do you see? You see a rainbow. Why is that? Because the light corresponding to different wavelengths is diffracted at different angles. And you know how to do that calculation, d sine theta equals n lambda, right? Remember that? So you're looking at the first or second or third order diffraction. So now what we're going to do, and incandescent light is just a glowing thing like a black body. And it gives you a continuous spectrum of radiation. Now we're going to turn off the light. I'm going to turn this light on. Now what I'd like you to do, the light is this is a tube with hydrogen gas in it. And if you look at the light, if you're seeing a smeared rainbow thing, turn your diffraction grating by 90 degrees, and you should see to the left and to the right of the light, you'll see the spectral lines coming from this emission. Let me stand back away so that I can see sort of what you're seeing a little bit better. You should be able to see a purple light, a purple one, or indigo, or violet, I guess you'd say, then a beautiful teal-colored one, blue, and then a bright red one as well, right? Does everyone see that? If you don't see that, turn it 90 degrees, and you're not looking at the light itself. Remember, look to the left or look to the right. If you look to the left, the purple one should be closest, then blue, then red. That makes sense, right? Because the angle corresponds to what? D sine theta equals n lambda. So the bigger lambda is, the bigger the angle is away from. And so the apparent distance away from the discharge tube is related to the wavelength. Okay, good. Now we're going to turn on a different one. This one is helium. Kind of cool. I count, an indigo, blue, blue-green, two of them there, sort of a yellow pair in the middle, and then red, and then a faint red one, right? Everybody see those? Each one of those lines corresponds to a characteristic wavelength emitted by helium. Here is, what is this one? Neon. Kind of a familiar discharge, but here you have lots and lots of lines, right? You can see dozens of individual spectral lines in there. Is everyone seeing it, or is someone just seeing still a rain? If you're seeing a rainbow, turn it 90 degrees. So neon obviously is has more electrons in it, more possibilities for energy states inside the atom. And then lastly, mercury. This one looks a little bit simpler in a sense. We've got yellow, green, and violet. So there now you've seen, really with your own eyes, that atoms do not emit light, atomic species do not emit light in a broad spectrum. They emit at very specific spectral lines. If you'll hand your diffraction gratings to the aisles, then I can come pick them up. Now this was already known in the late 1800s. And for hydrogen in particular, people studied the emission lines for hydrogen and knew exactly what their wavelengths were. And then, for example, Rydberg came along and developed a kind of magic formula that predicted what these lines should be. It was 1 over n1 squared minus 1 over n2 squared. And so the lines were labeled according to numbers, discrete numbers, n1 and n2, but nobody knew why, what that really meant or corresponded to. But it was known that there were discrete lines. Also, interesting fact, the atomic element helium was discovered really first not on the Earth, but by looking at the spectrum coming out of the sun. So here again is another observation that you can make in nature that just demands a quantum type explanation.